Now, think of you moving a bar magnet towards a solenoid, like so. Think of you having an ammeter and a light bulb or something. When you bring the bar magnet, let's say you're moving the bar magnet towards a solenoid, what would happen? Now, what Faraday observed was, now when the bar magnet was moving towards this circuit, when there was relative motion between the bar magnet and the circuit, he observed that there was a current, a deflection. But the moment the bar magnet stopped moving and there was no relative motion, there was no current observed and there was no light bulb lighting, right? Now, why is this, right? Did you ever think as to why this works this way? Well, when the bar magnet is brought towards the solenoid, how in the world do we get this light bulb to be lighting up? Did you ever think of it, right? It's a beautiful little concept. Now, when you bring the bar magnet to the solenoid, I don't know whether you have had this practical experience, but when you bring this bar magnet to the solenoid, you feel kind of a repulsion, because what happens actually is there's a current that's going on within this circuit that creates a north here and a south here when the bar magnet comes towards the solenoid, right? Okay, now tell me, if there's a north here that's created and when the bar magnet is coming towards the solenoid, there's a repulsion. You don't even have to think about the north. In the first place, when you're trying to bring this bar magnet towards the solenoid, you kind of feel a repulsion. You can experience this practically, right? Now, if there's a repulsion, the bar magnet is being pushed away. But you are bringing the bar magnet, aren't you, right? So when you bring the bar magnet towards the solenoid, you have to do work against the repulsive force. You experience a repulsion, therefore you have to propose a new force, right? You have to propose a force to combat this resistive force. The force that you apply is downwards, the force that you experience with the bar magnet is upwards. So you have to do work. You are doing work. You're doing mechanical work. You are applying a force in the direction of what? Your displacement. Work done is what? Force into displacement. If the force is in the direction of the displacement, work done is positive. Remember, work done, like if you have a force F, an angle theta, if the displacement is d, work done is what? F cos theta into d. Right? Now when cos theta goes to 0, we get F into d. When you go there and also the force is in that direction, you essentially do positive work. So aren't you doing positive work? Yes, you are. But the field is doing negative work. The force from the field is upwards. You are going down. So you're doing work against the field, the magnetic field, right? That's created here. So you're doing work against the repulsion. So whatever the work that you do has to be converted to something, right? It just cannot be destroyed. What happens then? The mechanical energy that you invest, the work that you do, is converted to what? Electrical energy in the circuitry. And that's why relative motion is required. Because if you don't feel a repulsion, you don't have to do work, right? So the circuit is inviting you to do work so that the circuit can light up, right? So that there can be current in the circuit. It's a beautiful little topic.